Hi there, this is Capacitance Lesson 2 and we're going to look at energy stored in a capacitor. So if you want to have a go at this, just pause, remember, for questions. So when fully charged, the 3 millifarad capacitor uses a backup for a memory unit, has a potential difference of 6 volts across it. The capacitor is required to supply a constant current of 2 microamps and can be used until the potential difference across it falls by 10%. For how long can the capacitor be used before it must be recharged? So on this one we've got a constant current. So we can simply use Q equals VC and Q equals IT and make them equal to each other. We've also got the 10% to look at, which we can just use the numbers in the question and then just multiply by 0.1 at the end to give us the correct answer for time. So we can do VC equals IT and then rearrange to get T. So T is VC over I. And then we just need to put some numbers in. So the voltage is 6, capacitance is 3 millifarads, so 3 times 10 to the minus 3. Divided by current, 2 times 10 to the minus 6. And then whatever that number is, just times it by 0.1. And that gives us a time of 900 seconds. Okay, let's get some information and then do some more questions. So energy equations for a capacitor, there's 3. So we've got energy is a half QV. Then we've got energy is a half CV squared. This one is used the most, I would say. And then the last one is energy is a half Q squared over C. So we've got 3 equations. So we've got the first one, the second one, and the third one. Make sure you've got those down. They should be on any data sheets, depending on an exam board. And then all we're going to do now is some questions just using these equations. So this one, calculate the energy stored when. So if you want to pause, and then I'll take you through them. A 10 microfarad capacitor is charged by 12 volts. So we've got capacitance and voltage. So the first one is going to be a half CV squared. So 0.5 times the capacitance, 10 microfarads, times 10, times 10 to the minus 6, multiplied by 12 squared. And if you calculate that, you'll get 720 microjoules of energy. If you want to get it into microjoules, just press the engineering button on your calculator, ENG. That should put you at that prefix straight away of the answer that you should get. Let's do the next one. So this one's we've got charge and voltage. So energy is a half QE. So we've got 0.5 times Q, which is 200 times 10 to the minus 6, times 6 volts. So the energy there is 600 microjoules. One more practice question. So we've got 0.05 microfarad capacitor receives 40 nanocoulombs of charge. So for this one, the energy is a half Q squared over C, or Q squared over C, over 2C. And then just put the numbers in. So Q is 40 nanocoulombs, so 40 times 10 to the minus 9, squared, divided by 2 lots of the capacitance. So 2 lots of 0.05 times 10 to the minus 6. And that gives an energy, a smaller energy, of 1.6 times 10 to the minus 8 joules. Hopefully that's okay. Let's move on to the next one. Initially, a charged capacitor stores 2000 microjoules of energy. When the PD across it decreases by 2 volts, the energy stored by it becomes 500 microjoules. What is the capacitance of this capacitor? Now there's some quick ways of doing this one. You could use a half CV squared. And figure out what happens to the voltage when the energy drops by a quarter. So if you've quartered the energy, you'd get half the voltage. And because a half squared is a quarter. and then figure it out that way. There's another way which I'm actually going to show you in more detail, as it's proper, so to speak. So this capacitor, regardless of how much energy we store in it, will have the same capacitance, because capacitance will be a constant on the same capacitor. So with the energy is a half CV squared equation, we have an equation for C. So we can rearrange to get 2 times the energy divided by V squared, and then make each scenario or situation equal to each other. So we've got 2 times the energy 1, divided by voltage 1 squared, equals 2 lots of energy 2, divided by the initial voltage now, V1, minus 2, because it decreases by 2 volts. And then remember to square this. The 2's will cancel as well. Energy 1 and 2 we know, so we just need to put some numbers in. So energy 1 is 2000 microjoules. I'll just put 2000, divided by V1, I'll just call it V, so V squared, equals energy 2 is 500, divided by V minus 2. And remember to square that as well. So what I'm going to do is take the V's to the left hand side and the numbers to the right hand side. So we're going to end up with V minus 2 divided by V. And remember, that's all squared. Equals, and we've got 500 over 2000, which is 1 over 4. Then what I'm going to do is square root both sides and then multiply, cross multiply. So we end up with, if we square root as well, so we've got the 4 will come up to the left hand side and we'll square root that to get 2. So we end up with 2, V minus 2, equals, and we took the V squared up to the right hand side, so we cross multiplied. And then we need to square out the V squared to give V. Then we've got 2V minus 4 equals V. Get the V's on the left hand side and the numbers on the right hand side. So 2V minus V, we'll just leave V, equals 4 volts. So the initial voltage is 4 volts. Now we can finish this off. So again, we've got the equation, energy is half CV squared. So C will be 2 times the energy divided by voltage squared. So 2 times the energy will be 4000 microjoules. Divided by V squared, the voltage we got was 4 volts, so that gives 16. So the capacitance would be 250 microfarads. Hopefully you followed that one. We're going to do another example, which is the same format, just different numbers. So initially a charged capacitor stores 150 microjoules of energy. When the PD across it decreases by 2.6 volts, the energy stored by it becomes 370 microjoules. What is the capacitance of the capacitor? So remember, we had the E equals half CV squared. And I'm going to make them both equal to C, make them equal to each other, but cancel the halves as well. So we end up with energy 1, which is 1500 microjoules, divided by the voltage squared, equals 370 microjoules, divided by the initial voltage, subtract the 2.6 squared. So let's take the V's onto the left hand side and the numbers onto the right hand side and then square root. So we're going to have V minus 2.6 over V equals, we've got the 370 divided by 1500, and then we need to square root. And 370 divided by 1500 square rooted is, let's use this number, 0.497. Then you can finish this one off if you wish. So I've got V minus 2.6 equals 0.497 lots of V. So I'm going to take that over to the left hand side, where we have 0.503 lots of V, equals, and on the right hand side we've got the 2.6. We'll just swap these over. So V would be the 2.6 divided by 0.503, which gives us a voltage of 5.2 volts. So the number's a bit stranger on that one, but hopefully that went okay. Let's have a look at the next one. So you want to pause and have a go. A 2000 microfarad capacitor and a 20 microfarad capacitor are charged so that they store the same energy. The PD across the 2000 microfarad capacitor is voltage 1, and the PD across the other capacitor is voltage 2. So what is the value of the ratio V1 over V2? So it says that they store the same energy, so we can say that energy 1 is equal to energy 2, and energy is a half CV squared. So if we write half CV squared equals half CV squared, the halves will cancel, so it's just capacitor 1 times V1 squared equals capacitor 2 times V2 squared. So we just need to put some numbers in. So capacitor 1 is 2000 microfarads times V1 squared equals capacitance 2, which is 20, times V2 squared. And the question is asking for V1 over V2 squared, so we just need to do some rearranging. So V1 over V2 squared is equal to 20 over 2000. And 20 over 2000 is 0.01. Well done if you got that one. Let's do the next one. So last question. A capacitor of capacitance C has a charge of Q stored on the plates. The potential difference between the plates is doubled. What is the change in energy stored by the capacitor? So if you want to have a go, please pause. So a couple of things on this one. The potential difference is doubled. So we need to see what happens to the energy if we double the potential difference. So energy is half CV squared. If we double the potential difference, we get 2 squared, we get 4 times the energy. So the equation for energy stored on a capacitor is Q squared over 2C. So that'll be the initial. And then the energy after the potential difference change would be 4 times the energy. So that would be 4Q squared over 2C. And the trick to this question is it's asking for the change in the energy. So to get change in energy, we need to do the final energy, which is 4Q squared over 2C. Subtract the initial energy, which is Q squared over 2C. Same denominator, so we just need to subtract the numerators. So that gives us 3 lots of Q squared over 2C. So the answer is C. So I hope that went okay. Hopefully that's helpful. Thanks for watching. I'll speak to you soon.